When making radiographs, photons enter the patient and interact with the hard and soft tissues. For diagnostic X-ray photons, these interactions occur via Compton scatter, photoelectric absorption, and coherent scatter. In this video, I will describe these interactions in more detail with their implications for diagnostic imaging. Photoelectric absorption is critical in diagnostic imaging. It is the basis for radiographic image formation. In photoelectric absorption, an incident photon loses all its energy to an inner orbital electron and ceases to exist. The energy absorbed by the electron is expended to overcome its binding energy, and the remainder remains as its kinetic energy as it is ejected from the orbital. The ejected electron, called photoelectron, loses its energy through subsequent ionizations. The probability of photoelectric absorption is directly proportional to the third power of the atomic number and inversely proportional to the third power of energy. In this demonstrated situation, photons incident on materials A and B have equal energies. Based on this information, we can conclude that the atomic number of material A is lower than that of material B. Differences in photoelectric absorption provide us with radiographic contrast. As seen in this radiograph, the differences in the photoelectric absorption allow us to resolve the dental hard tissues, cortical and trabecular bone, and the air cavities. So, to summarize, photoelectric absorption is good. It provides us with the radiographic image. However, it does cause ionization and so has the potential for biological detriment. The next interaction is Compton scatter. Compton scatter occurs when a photon interacts with an outer orbital electron. In this interaction, the photon loses only part of its energy to the electron. Following the energy loss, the photon is scattered in a direction often different than its original path. Similar to photoelectric absorption, Compton scatter also causes ionization of the target atom. The occurrence of Compton scatter has important practical implications. Scattered photons travel in all directions and may exit the patient and strike the image receptor. These photons carry no useful information and degrade the image by reducing image contrast. Scattered photons travel varying distances within the patient's tissues and cause ionizations. This internal scatter increases patient radiation dose and often exposes organs and tissues outside of and distant from the path of the primary beam. Importantly, scattered photons that exit the patient can expose the operator. The third interaction is coherent scatter, which occurs only with low energy photons less than 10 keV. In this interaction, the energy transfer excites all of the electrons within the atom. As the atom returns to its ground state, it emits a scattered photon of the same energy but at a different angle from the path of the incident photon. Because no energy is transferred to the biological atom, no ionizations are caused. Coherent scatter is less significant than the other two interactions and accounts for only 7% of the total interactions in the dental exposure. So the key take-home points: photoelectric absorption. Its probability depends on the atomic number. It contributes to image formation but causes ionization and thus biological damage. Compton scatter causes scatter radiation which degrades the image quality and also contributes to patient exposure. It causes ionization and thus has the potential for biological damage.